Okay, ready to start.
All right, so this is talk about numbers. Big numbers, numbers so big. At least I have a difficult time just comprehending how big they are.
Just a chair.
One of those tables, the calculator said, hey, actually 2 times 2 and 4. It said times 2 equals. You get a nice big error. And that made me happy. I'm not sure why. I go to college and do some programming like factorial functions, things like that. 2 factorial, 3 factorial. Hey, what happens if you put 100 in here? I got one with episode. And I ended up studying about that a little bit. So this is who I am. I'm Beaver. Going known as Grahm, email address, all that good stuff. What is big? This is the first question I always get asked. Is to say big numbers. Well, what do you mean by big? Well, we've got some fairly large numbers that are commonly 64-bit numbers, 128-bit numbers. The canonical big number is Google, which has 100 digits. It's nice to try to get a scale of some of these numbers. So 256. 256 is your standard DES key. It's what the government used for years and years for encryption systems. The top computer on the top 500 supercomputer list right now is Japan's K computer, and it can do 256 operations in approximately 4 seconds. So if you use a 56-bit key, that's not going to help you much. But 2 to 56 isn't that big. 2 to 64 is the largest operation that most computers can do. They can do 128-bit arithmetic, but they're doing it as multiple 64-bit arithmetic. So if you go over 2 to 64, you have to write custom code anyway. When you move up to 2 to the 128, most places you're going to see this is an IPv6 address. Now, a while back, I worked for a router company, and we were implementing some of the IPv6 code, and we thought, how big is an IPv6 address? I wonder how many atoms are in the sun. Just happens to be one of the guys I work with is a physicist. So we figured out approximately mass of the sun, moles, hydrogen atom. An IPv6 address can address approximately every atom in the sun. Approximately. It's a little shy, but so 128-bit address every atom in the sun. And that's a big number. 2 to 256, this is used in encryption quite a bit. The Red Book by Schneier, or Brian Zimmerman, I forget, Applied Cryptography. He has a great discussion about 2 to 256. The discussion was, if we want to do a brute force of a 256-bit key, we can take the sun, roll it back to when it was first born, build a Dyson sphere around it, capture all the energy output of the sun. Then by the laws of thermodynamics, we can determine how much minimum amount of energy to enact a state change. And if we sped the sun up all the way to it burned out and was dead, we can't count 2 to 256. Not that many bit flips. That's not even counting to any computation. So effectively, a 256-bit number, you can't run that many computations. It's not possible. Then we get into, well, what is the extent of numbers in the physical world? There's this guy named Planck. He came up with Planck time, Planck length. Based on the current understanding of physics, it's the minimum amount of distance that can be measured. If you have 2 particles closer than this, we can't tell the difference between the 2 positions. And it's roughly 10 to the 20 smaller than the width of a proton. Now, if you take that and make it a volume, we have a Planck volume. That's the smallest space that we can determine in the current understanding of physics. Then we use the visible universe. So the universe is a certain age, light travels at a certain speed. There's only a certain volume that we can detect. Yes, cubic meters. But so we can compute, or we can individually identify every single cubic or Planck volume in the observable universe. And that's roughly a 600-digit binary number, or 300 decimal digits. So if you want to measure anything in the real world, 256-bit numbers is roughly good enough. You don't need any bigger than that. But numbers get much bigger than this. Mercian crimes of the form 2 to the n minus 1. The largest one found so far is, let's see here, 4 million. 2 to the 4 million. 4 million digits. You convert it to decimal, you get about 12 million decimal digits. Skews number is kind of interesting. Prime numbers are entertaining. The distribution of prime numbers, you figure wouldn't be that difficult, considering the first one is, well, it's every 2. But then you have to take that out, and then it's every 3. Then you take that out, it's every 5. You take that out. They still haven't been able to figure out how to do this stuff. But they have a function called the prime counting function, which is the distribution of prime numbers, which they have to compute iteratively. But we can approximate it. We can approximate it with the logarithmic integral. And there was this guy named Stu, and he calculated that the logarithmic integral and the prime counting function, they cross. And the point that they cross was either 10 to the 10 to the 10 to the 34, which is 3,000 some digits, or 10 to the 10 to the 10 to the 936. Whether or not the Riemann zeta function was true or false. Now, an even weirder thing is the fact that they cross, but they cross again. And these two functions cross an infinite number of times, and at very, very large positions. To this date, they still haven't found the exact point where the two numbers cross. They've gotten it fairly close, still can't get it done. So we fast forward a little bit, we get up into Church and Turing. Church is the guy who invented quantum calculus. Lisp, all that kind of stuff, mathematical approximation, computation. And then we had Turing, his version of the Turing machine, a finite state automata, changes states, and an infinite tape. And these two guys went back and forth for quite some time, trying to figure out what is computable. We had recursion on one side, we had state machines on the other, and they came down to something called primitive recursion. Primitive recursion is a computation that can be done with finite bounded loops. You can't have any loops that you don't know how many times they're going to iterate. And the guy that determined this was named Ackermann. He caused a whole lot of trouble. In fact, he caused computers to crash decades in the future. He showed that primitive recursion was not the same thing as computable. So there were functions that can be computed but could not be done with primitive recursion. He started out with a sequence of operators. Increment is just take the next, it's the sequence function, counting, 1, 2, 3, 4, 5. Addition is iterated counting. If you add 5, you just count by 5. Multiplication is iterated addition. Multiplying by 5 is adding 5 times. Exponentiation is iterated multiplication. Now this is a very nice construction of these operators. But this means that we can extend this sequence. After that, they named it tetration, pentration, there's this whole, or pentation. There's a whole series of operators that come after this. And we have the Ackermann hierarchy. The Ackermann hierarchy is the first operator, 1 plus 1. Second operator, 2 times 2. 3 raised to the 3, 4 tetrated 4, 5 tetrated 5. And we can see some of the numbers here. First one is 2, 4, 27. We get a big number. The fifth one has thousands, or 100,000, million, billion, trillion, 41 quadrillion digits. Now, you can't write a number that has 41 quadratic digits. It can't be done. But we do a notation for it. Now, a lot of you have heard of this guy named Knuth. Wrote some books, tend to be popular. He created a notation for writing very, very large numbers, and it's based on the Ackermann hierarchy. He has an up arrow where A with one up arrow, B is exponentiation. 2 arrows is tetration, 3 arrows is pentation. And now we can write in bigger numbers without having to write 43 quadratic digits. And there is a construction where you can take 2 arrows devolves into A arrow B arrow B. But now we have 3 up arrow 3 is 27. You do 2 up arrows, you get a great big number. 3 up arrows, we end up with that. Which, by the way, that will crash your laptop. And that's only with 3 arrows. You can easily write 3 arrow 103, end up with a really big number, take your laptop out even better. This is my new favorite number. Now, the interesting thing about this is with 1 arrow, this is with 2 arrows, this is a string of 100 100s in a column, exponentiation power. With 3 arrows, it is 10,000. So, by the time you get 100 arrows, this is completely uncomputable, but we can write this number. It's a number so big, I can't imagine it. The way that Ackermann proved that primitive recursion and computability were different was through the Ackermann function. The Ackermann function grows much, much faster than any other primitive recursion function. Factorials, hyperfactorials, exponentiation, this dwarfs all of those. The first digit is the one we really have to be careful of. When we start iterating through the Ackermann function, we get 4, 5, 9, 61, 2 to a 19,000 digit number minus 3. And a lot of people ask me, they say, the Ackermann function, okay, well, this is a cool function, but what good is it? Well, it turns out it's really good for crashing compilers and for compiler benchmarks. Now, large numbers actually do come about in the real world. Ramsey theory is one of the places where we see very, very, very large numbers, and it's through actual practices. Ramsey theory is all about how it works. It's sort of like the birthday paradox. If you have a large enough set of items, any given property you want will become true. A great example of this is the Bible codes or the Torah codes. You have a large enough book, you can find any word you want in any arrangement. You just have to have a book that's long enough. So, Graham's number is an example of a very, very large number. In fact, I'm not sure if it still is, but it was the Guinness Book of World Records' largest number for many years. And this is if you take a cube and you color each of the edges. You want to know, now we have a cube, we have a hypercube, which is a 4th dimensional cube, you have a 5th dimensional cube. How many dimensions of cube do you need before it is impossible to color the cube without having a one face that's all the same color? You might think that, okay, what the heck is the use of that? Well, the graph coloring is used a lot in scheduling algorithms, in compiler optimization, register allocation, all those sorts of things. And Ronald Grahm figured out that he knew that the dimension of the hypercube was greater than 6. He also calculated the largest bound of this. Now, we have Knuth's up arrow notation with an up arrow and a number indicating how many arrows. Well, Graham's number has more arrows than Planck volumes in the visible universe. So you can't even write the number of arrows. nonetheless Graham's number. But we do know that it ends with 195387. There was an XKCD comic a little while back. Makes a whole lot more sense if you know what Graham's number is. And A is the Ackermann function. So if you feed Graham's number to the Ackermann function, well, you're going to crack your laptop. This is not the only way that they use to represent large numbers. There's this guy named Conway that said, new subarrow notation is really cool, but it can't represent large enough numbers. Having 34,000 up arrows, that's no good. So he has a series of chained arrows. Conway's chained arrow notation. A arrow B is exponentiation. A arrow B arrow C is the hyperoperators, just like his up arrow. But if you put 4 arrows, it gets really, really strange. It actually ends up iterating based on the second term. I still haven't completely figured this one out. I can compute it though. So if you have 4 3s, chained arrow, it expands. It expands down, expands down, expands down. You actually say, to reduce the last digit by 1, you replace the next to last term with the entire sequence with the second to last reduced by 1. I'm not sure how he came up with this. I think he was probably smoking crack at the time, but it allows you to represent some really large numbers. Now we can go back to Turing for a minute. There are some, even with Graham's number, Conway's chained arrow numbers, there's some numbers that are even, they're not necessarily bigger, they're more difficult. A Turing machine is essentially a piece of tape and some rules, where you say what number is on the tape. Based on that number and what state, we know I want you to output a 0 or a 1. I want you to move right, left, or stay where you're at. I want you to move to this next state. Now, if you have n states, for example, only one state, you will have inputs of 0 and 1, outputs of 0 and 1, and what state you want to move to, which is either yourself or the halting state. We run into a bit of a problem whenever we want to determine whether or not a Turing machine finishes. The halting problem is all, given a Turing machine, will this machine finish or will it iterate forever? It was proven that this is not computable. We can run the machine, but we can't prove whether or not it's going to finish or not with a program. The busy Beaver numbers are based on, if we have a Turing machine with, let's say, 2 states, what is the largest number of ones that it will output and still finish? A couple of these have been computed. A 1-state busy Beaver is going to output 1, 1. 2-state busy Beaver outputs 4. 3 outputs 6, 4, 13. Now, just the 5th number in this sequence, we haven't been able to compute yet. We know it's greater than 4098. Busy Beaver 6 is highly likely we'll never be able to figure this one out. But it is 3.514 times 10 to the 18,000. 10 to the 18,000 steps that this machine makes and still finishes. Which is a little odd considering we can't do 2 to the 256 calculations, but we know that this takes 10 to the 18,000 steps and finishes.
What is busy Beaver? What's the calculation?
So it's simply run the Turing machine, see how many ones it outputs and stops. So it's the maximum complexity of a Turing machine with that number of states. Once it gets into a loop, it's no longer interesting. But with only 6 states, we get into very, very large numbers. Those 6 states actually generate a massive amount of output and still terminate. And that's all I got. Any questions?
What practical things should people do with this?
So there's two answers to this. One of which is anything over 2 to the 617 is not reasonable in the real world because there's just nothing physically that much. But Ramsey theory, for example, is the things that we learn through Ramsey theory allow us to build better scheduling algorithms, allow us to build better microprocessors. Because you can say, given a function of n inputs, what is the minimum number of registers that I'm going to need where I can hold all the local variables? And that's what Ramsey theory is all about. What is the minimum set size that makes a certain property true? So, number theory. But it does have practical applications on the smaller level.
You said Graham's number was the record holder for largest number for how many years? And
well, it's the largest practical number used in a mathematical proof.
okay, so it's still presently the largest number used.
I'm not sure. There were some other contenders, but they were starting to play hard and fast with the rules of saying this was practically used in a mathematical proof, whereas Graham's number is actually the solution to a problem in Ramsey theory. The last I knew that they had submitted an application to Guinness. Whether or not it went through, I'm not sure.
What's your least favorite number?
1. It's the loneliest number. All right, well, I'm done. Thank you all very much.
For anybody interested in the whole Busy Beaver thing, there was actually a video somebody put on YouTube a while ago where they actually built a Turing machine-like thing that actually will look, move, erase the number, move, you can see the state and everything, and it'll actually do these operations within the context. It's like a dry erase marker and an eraser. So it's literally writing with a robotic arm, writing a 1 down using a dry erase marker.
The interesting thing I find about Busy Beaver is how do you actually compute something that takes 10 to the 18,000 steps when you can't compute 2 to 56 operations? And you end up getting into a lot of very unusual optimizations to be able to compute large numbers of state transitions with only a few computations. And there have been papers and papers and papers written on this.
I think one of the interesting things about the function specifically is at this point it's demonstrated to grow faster than any other
it grows faster
function.
than all of the Ackermann function. It grows faster than the Ackermann hierarchy. And the worst part about it is it's not computable. So it grows really fast, but we can't actually tell what the number is. The way they actually have to compute the number is you have to iterate all the machines. So you build every possible machine, you run each one of them, you find out which ones never terminate because they don't have a termination state. Then you run them all until they terminate. You get a set that haven't terminated yet. Then you run the ones that are left until some of them terminate. Then you run what's left until they terminate. Then you run what's left until they terminate. You end up with a set that keeps running. And you have to figure out whether or not they're going to keep running forever or they will eventually terminate. You can do mathematical proofs saying it is impossible for that machine to get into a state where it will halt, and then you can cancel that way. You end up with papers on individual Busy Beaver machines.
Yeah, we can cancel those machines, or physical machines, or is it something that's just function written in the program?
It's a finite state machine, so it's a mathematical model.
Could you turn your mic back on?
So the example of the one-state Busy Beaver is simply, there is only one state, so you can only be in one state. If I see a 1, I can either output a 1 or a 0. And I can move right, left, or stay where I'm at. I have to go back to state 1. For it to terminate, one of the two transitions from in state 1 with an input of 1 or in state 1 with an input of 0 has to go to the halt state, which means the other one goes to state 1. And there are YouTube videos of the mechanical models and of teaching them. The nice thing about Turing machines, why they're taught at all, is because they want to be very simple models of computation, and anything that is computable can be implemented in a Turing machine. So you can do these things and do algorithmic sorts and factor prime numbers with these very simple machines that just doesn't move right and left and output ones and zeros. So it's the basic model of computation. Except, well, the other model is lambda calculus. There's 2 branches of computer science for computability.
Peter Crummon's at catonmat.net has a good post about busy beavers with a Python script that he built that actually will run them. And actually, it outputs all the states as it's going through. So it'll actually, as you iterate through a step, the script will actually print out essentially what the tape looks like at any given step.
Right now, they call it the Busy Beaver competition, and they're continually trying to get the largest known Busy Beaver within a given size. Even if you're talking about 10 to the 18,000 states, that's that many ones output. So you have to get clever about how you store the tape, and you can optimize state transition. You can say, when I'm in a certain state and I see a sequence of ones, I know it's going to flip them all to zeros. Well, if you store one length encode your tape, so there are 37 ones, you can just change one digit and say, okay, that's 37 zeros, move to the next chunk. Anyone else? Okay, thank you.